So here's our first introduction to the periodic table. We've already shown you already that the periodic table is arranged with their elements in order of increasing atomic number, right? Where the atomic number defines the element and is associated with the number of protons in the nucleus. We're going to discuss a lot of the patterns and a lot more information in the periodic table in subsequent chapters. So right now we're just going to focus on sort of the bigger scope in the periodic table, and we will wait till we get to quantum theory for an interpretation of the patterns and trends and why the periodic table is organized the way it is. First of all, about 75% of the elements in the periodic table are metals. So they're shown by this color. Here's a little staircase dividing line between the metals, shown here, and the non-metals in this color, shown here. So metals have the property of when you pound on them, they're malleable, so they tend to form thin sheets. At a given temperature, you can draw them into wires, so that's a property of ductility. They conduct heat and electricity pretty well, and all of the metals are solids at room temperature with one exception. Element 80 is element mercury. It's a liquid at room temperature, and gallium is almost a liquid at room temperature. Solid gallium will melt in your hand. Now, the nonmetals are either solids, liquids, or gases, depending on which element you're talking about. The solids do not conduct heat or electricity well, as opposed to metals, and you cannot pound them into thin sheets or draw them into wires. Instead, when you pound on them, they just break. They're very brittle. And then the dividing line with the elements boron, silicon, germanium, arsenic, antimony, and tellurium are so-called metalloids. So these sort of have properties of both metals and nonmetals. Now, the reason why we're bringing up this point right now, metals, metalloids, and nonmetals, and it's very, very important for you to remember which ones are metals and which ones are nonmetals and which ones are metalloids, is because in sections 6 and 7 of this chapter, if we give you a formula, you need to be able to tell whether or not the compound is a molecular or ionic. And as a first point, you need to be able to determine whether the elements in the formula are metals or nonmetals. So in addition to that, the structure in the periodic table, the elements are listed in rows, right, which we call periods. So the first row consists of just 2 elements, hydrogen and helium. The second row has 8 elements, going from lithium to neon. The third row consists of the elements sodium to argon. The fourth row, potassium to krypton. The fifth row, rubidium to xenon. Sixth row, cesium, barium, and then as well as this row right here is inserted between barium and lutetium. The first row right here of elements are called the lanthanides. Lanthanum is the first element there, from lanthanum to ytterbium, and then that 6th row is completed at radon. The 7th row begins at francium, radium, and then we insert the second row of elements right in here. These are called actinides, and nearly all of them are radioactive. In addition, the elements are organized in terms of columns, right? The vertical columns are called groups, and some of them have common names that you need to know. So for example, the group 1 elements, excluding hydrogen, are called the alkali metals. The group 2 elements, from beryllium on down to radium, are called the alkaline earth metals. The group 16 elements, from oxygen, sulfur, selenium, tellurium, and polonium, are called the chalcogens. Group 17 nonmetals, fluorine, chlorine, bromine, iodine, and astatine, are called the halogens. And then finally, the elements that close out the end of the periods are called the noble gases. These are the group 18 elements. So these common names and their associated groups you need to know for the next coming exam. Now, one other important point about elements that are organized in a group is that they have similar reactivities. Not identical, but similar. For example, the chalcogens oxygen and sulfur both form a compound with hydrogen in a 2-to-1 ratio, H2O and H2S. Now, they're certainly quite different compounds. H2O, or water, is a liquid at room temperature and is essential for life. H2S is a gas at room temperature and it is highly toxic. So toxic that our noses are very, very sensitive to even the tiniest amounts of hydrogen sulfide that are present because it's so toxic. So shown here are the elements that are necessary to sustain life on our planet as we know it. Our bodies are about 70% water, so that's H2O, right? You just need hydrogen and oxygen to make water. Throwing carbon in addition to hydrogen and oxygen, you have all that you need to make carbohydrates, right? Starch and sugar. If we add nitrogen in, we have all the elements that we need, all right? Hydrogen, carbon, nitrogen, and oxygen. That's all you need to make the amino acids, the fundamental building block for proteins. So these constitute about 96% of the entire body mass. In addition to that, shown in green, we have some macronutrients. Phosphorus is important. In addition to hydrogen, carbon, nitrogen, and oxygen, you have what you need to make two very important classes of molecules. One are the nucleic acids, RNA and DNA, right, which have the instructions for sustaining life, as well as phospholipids, which are the main component of cellular membranes. Sulfur is also important because there are two amino acids that require it, methionine and cysteine. And the metals here, sodium, potassium, and magnesium, are important for a variety of different cellular functions. Sodium and potassium particularly for neural activity. Calcium, along with phosphorus and oxygen, right, makes calcium phosphate principal component of bone. And in addition, in even lower amounts in the macronutrients are trace elements composed of these metals here, the so-called transition metals, which form active sites of a special class of proteins called enzymes, more precisely metalloenzymes that catalyze very important reactions necessary to sustain life. In addition to the transition metals, we also have some main group elements, boron, fluorine, silicon, arsenic, selenium, tin, and iodine that are also needed. In the next two sections, we're going to be looking at how to distinguish between compounds that are molecular and those that are not, that is, those that are said to be ionic. So we'll begin by looking at the molecular compounds. And one thing that you're going to have to get used to doing is looking at the formula, right? The formula is very abstract, but it has a lot of information buried in it. For example, the elements hydrogen and oxygen, we've told you before, are molecular, and they consist of two atoms that are bonded together. In the case of hydrogen, it's two hydrogen atoms stuck together and two oxygen atoms stuck together. And so when a chemist looks at these formulas, immediately the picture that pops up in one's head is this. So this is something you're going to have to get used to, right? The smallest piece of the element hydrogen and the smallest piece of the element oxygen that has all of the physical and chemical properties of these elements are shown by these representations, right? Two atoms stuck together in each case. All right, so we represent that as a formula, H with a subscript 2. So these molecules are said to be diatomic for that reason. Now if we look at some compounds, remember a compound consists of two or more different elements that are molecular. Here's an example of two different compounds consisting of the elements hydrogen and oxygen, right? So water has a 2-to-1 number ratio, not a mass ratio, but a number ratio, 2 hydrogen atoms for every oxygen atom. In addition, we see a well-defined structure. Every water molecule looks like this. An oxygen atom is embedded in between the 2 hydrogen atoms, and it's not linear. There's an angular component to this molecule, and every water molecule looks the same. There's another compound of hydrogen and oxygen, and that's called hydrogen peroxide. It has a different formula, right? In this molecule, there are 2 hydrogen atoms and 2 oxygen atoms. So we write the formula here, H2O2. If we look at some other compounds, in this case, 2 different compounds of carbon with oxygen. There's carbon monoxide, which has the formula CO, so it's every molecule has just 1 carbon atom bonded to 1 oxygen atom, and carbon dioxide with a formula CO subscript 2 has a carbon in the center, and on each side of the carbon atom are 2 oxygen atoms. So this is again an island consisting of 3 atoms that are stuck together. Every carbon dioxide molecule looks like this. Here are 2 different compounds of carbon and hydrogen, so there are many, many, many different compounds of carbon and hydrogen. These are just 2 examples. The first one is methane, also known as marsh gas or swamp gas, is a fuel. And it consists of a carbon atom in the center with 4 hydrogen atoms equally spaced about the carbon atom, and the formula is CH4. Now, shown here is a molecule called ethylene consisting of 2 carbon atoms and 4 hydrogen atoms. So we write the formula C2H4. And this is a fundamental building block for many plastics called polyethylene. So if we actually were to bring another ethylene molecule, we can make a carbon-carbon bond between them, and we can continue to do that, string ethylene molecules together to form what we call a polymer. So polyethylene, the rigid form or high density form is used to make milk jugs. The low density form is stretchable and is used to make plastic wrap like saran wrap and things like that, food wraps. Now, if you look closely, I hope you see that there's a pattern here, right? That all of these elements are nonmetals. So this is the first rule of thumb that you need to know to make a prediction if you're given a formula of whether or not it's going to be a molecular compound or not. If all of the elements in the compound are nonmetals, more than likely it's a molecular compound. So far we've been talking about just looking at what's called the molecular formula, which gives you all of the different atoms in a molecule. So hydrogen peroxide has a molecular formula H2O2. Every molecule has 2 hydrogen atoms, 2 oxygen atoms. We can distinguish the molecular formula from what's called the empirical formula. And the empirical formula gives you the simplest whole number ratio of all the different elements in a compound. So, for example, the empirical formula for hydrogen peroxide, right, would just be a 1-to-1 hydrogen-oxygen ratio, HO. The reason why we're bringing this up is because in the next chapter, we're going to show you that if you make a compound in the laboratory and you send it out for what's called elemental analysis, you get back information of the mass percentages of all the different elements in the compound, and ultimately from that information you can deduce a formula. But it won't be the molecular formula necessarily. It will always be the empirical formula. So it's important to make this distinction now. So in addition to the molecular formula and the empirical formula, we can also write what's called the structural formula. Now the structural formula provides the more detailed information of how the atoms are actually arranged, right? When you just write the formula H2O2, it may not be clear how the atoms are bonded together. We will show you later on in this class that we can predict actually how the atoms will be arranged. And we'll go through rules for how to generate these structural formulas. But just for now, if you're given a structural formula, you should realize that these lines here just basically denote linkages between the different atoms. In addition to the structural formula, we have two other representations for models for the molecular compounds. One's the so-called ball and stick model. The other one is very similar to it. It's called the space filling model and is a better representation. Here you can see that the atoms are actually fused together, right? You can see the atom connectivities, and it gives you some idea of how large the molecule is. Molecular compounds, and we stated that in general, if the elements in the compound are composed of nonmetals or even metalloids, usually the compound is going to be molecular. If the formula has elements of both metals with nonmetals, generally the compound will be ionic. All right, so what are the components then of an ionic compound? Are these ions. So what are ions? Well, the positively charged ions are called cations. Negatively charged ions are called anions, and in a compound formula consisting of ions, the numbers of cations and the numbers of anions must be present in such a way that the entire formula is electrically neutral. All right, so that the net charge of all of the ions in a compound, when you add them all together, has got to come to zero. So, how are positively charged ions formed? Well, you take an electrically neutral atom, in this case a metal, and the metal gives up an electron to the nonmetal, so that the metal becomes positively charged, becomes a cation, and the nonmetal becomes negatively charged, an anion. So here's an example of an ionic compound. If you look at the formula, NaCl, Na, sodium is a metal, chlorine is a nonmetal. When a sodium atom combines with a chlorine atom, an electron is transferred from sodium to chlorine. Since the sodium atom loses an electron, it becomes a cation, a positively charged ion. The electron goes to the chlorine atom, so it becomes Cl- with a -1 charge and is an anion. Now, we'll show you on the next slide a simple way to memorize that sodium always is +1 when it forms an ionic compound, and chlorine always has a charge of -1 when it forms an ionic compound. So, the simplest whole number ratio is 1:1 to make this electrically neutral. So we have an example here of an empirical formula, right? Let's look at a more complicated example, that of calcium bromide. It turns out that, well, first of all, let's look at the formula, right? Calcium is a metal, bromine is a nonmetal, so we would predict an ionic compound, and it turns out that when calcium forms an ionic compound, it's always +2, and bromine is always -1. Now, since calcium is always +2 and bromine is always -1, we need to have 2 bromides for every calcium to make the compound electrically neutral. That is, if we add up the charges, +2 plus -1 plus -1, we get 0. So the simplest whole number ratio in which we can write the formula to make the charges add up to 0 is a 1:2 ratio. If we look at this example, aluminum oxide, again, aluminum's a metal, oxygen is a nonmetal. It turns out that whenever aluminum forms an ionic compound, it's always +3. Whenever oxygen forms an ionic compound, it's always -2. And so when you look at these, there are all kinds of gimmicks that allow you to generate the empirical formula for the ionic compound. Here it's Al2O3. I'm not going to talk about those. They're in your textbook. Instead, I want you to focus on how many components, when you add them together, will give you a charge of 0. If we just start off with 1 aluminum plus 3 and 1 O2 minus, and we add together the charges, what do we get? Plus 1. Well, it's not electrically neutral. So let's just start adding fragments. Let's add one of each. So we have 2 aluminum ions, that would be a total of plus 6. 2 oxide ions, that would be a total of minus 2 plus minus 2 or minus 4, right? Well, plus 6 minus 4 gives us plus 2, so we're still not done. But now we realize that if we just add another oxide, 2 minus, we'll have everything that we need. So we need 2 aluminum ions and 3 oxides to give us an electrically neutral compound, Al2O3. You can always figure out the empirical formula, electrically neutral for an ionic compound, just by a simple consideration of thinking about the pieces and adding them together in the simplest whole number ratio so that the total charge is 0. All right, now on the previous slide, we told you that sodium is always plus 1, calcium is always plus 2, aluminum is always plus 3 when they form ionic compounds. We said that chlorine, shown here, is always minus 1, bromine is always minus 1. Right? So the simplest way to remember this stuff, since you're going to be given a periodic table on your exam, is to locate the place where the metal is in the periodic table. So here are our metals, and shown here are just the metals for the alkali metals, right? The group 1 and the group 2 metals at the alkaline earths. Whenever these elements form an ionic compound, that is, they combine with a nonmetal, one of these, the charges are always plus 1 for the alkali metals and always plus 2 for the alkaline earths. You can just look in the place in the periodic table, and they will always give you the charge. Plus 1 here, plus 2 here. In addition, in the group 3, aluminum is always plus 3. Then there are only 2 others that you need to memorize. Zinc, when it forms an ionic compound, is always plus 2. Silver is always plus 1. Now, there are lots of places here in the metal portion of the periodic table where we don't have the element with its charge written. And that's because when these elements form an ionic compound, the charge can be different. And so we're distinguishing between what I call type 1 metal ions. Those are elements that always form the same charge, no matter what. Whenever they form an ionic compound, you're guaranteed to have those charges. Type 2 metal ions, the charge is variable. Okay, so we'll talk about how to figure out the charge of those given a chemical formula at a later time. For right now, I just want you to memorize these are always plus 1, these are plus 2, aluminum's plus 3, and then zinc and silver are plus 2, plus 1 respectively. Now, let's look at the nonmetals. When they form an ionic compound in combination with a metal, the halogens, right, the group 17 elements, are always minus 1. Then if we move 1 over to the left, the chalcogens are always minus 2. And then we go over 1 more, right, to the group 15 elements. Nitrogen, phosphorus, and arsenic are always minus 3 when they combine with a metal to form an ionic compound. So you just memorize these from their place in the periodic table. All right, so we've already told you previously that if you look at the formula of a compound, say SO2, which is sulfur dioxide, NH3, which is ammonia, and CCl4, which is carbon tetrachloride, in all of 3 of those cases, all of the elements are nonmetals. So you should predict that the compound will be molecular. When we look at SiH4, this is silicon tetrahydride. Silicon is a metalloid, but still you would predict this to be molecular. You won't be right every single time, but for the purposes of this course, in particular for your exams, this is what you're going to use as a prediction for what constitutes a molecular compound. Now, for ionic compounds, right, we said that you need a metal combined with a nonmetal. We've given you two examples already, sodium chloride and calcium bromide. Both sodium and calcium in this case were type 1 metal ions, and they are defined with +1 and +2 charges always. In this particular case, Mn is manganese, right? It's a metal, and oxygen is a nonmetal, so we have an ionic compound again. In this case, we also know that oxygen, right, always forms a -2 charge. And since we have two of them in the formula, that's a total of -4. That allows us to figure out what the charge of manganese must be. Take a moment to think about it. This is not one of the type 1 metal ions. This is a particular case where the charge of the manganese is defined in the compound by how many of nonmetals are around it. Okay? Well, if you have a total in the formula -2 per oxygen and two of them, that's a total of -4. For this to be electrically neutral, the manganese must be have a charge of +4. There are other compounds with manganese and oxygen. For example, MnO, the manganese would have a charge of +2. Still an ionic compound. Now, just as the metalloids serve as a transition or a bridge between properties of metals with nonmetals, something is similar in terms of compounds, in terms of their bonding. The bonding can be either purely ionic, where the constituent components are well-defined ions, positive and negative, with well-defined charges. Those are purely ionic compounds. Molecular compounds are formed by sharing of electrons, and in which case if the sharing is equal, the charges on the atoms are 0. But the truth is, most compounds are neither purely covalent, where the charges on atoms are 0, or purely ionic, with well-defined discrete charges. They're somewhere in between. And we'll revisit this topic in a bit more detail in Chapter 8. All right, so on your next exam, one of the things you're going to need to be able to do is that if I give you the formula for a compound, you should be able to deduce whether or not it's a molecular compound or a non-molecular compound, that is one that's ionic, right? So go ahead and get out a periodic table, because you're going to get one on the test, and use it to deduce the following situations. So if you have this compound, this is silicon tetrachloride, is it molecular or ionic? Okay, well, since silicon is a metalloid and chlorine is a nonmetal, your prediction should be that it is molecular, and indeed it is. The next one, LiF, is lithium fluoride. So lithium is a metal, fluorine is a nonmetal, so you should predict that it's an ionic compound. What about this one? BaCl2 is barium chloride. All right, so you'll find barium, Ba, is one of the alkaline earth elements, so it's in the second group. So it's a metal. Chlorine is a halogen, nonmetal. So we have metal with nonmetal, so this compound is ionic. What about this one? This compound name is diborane. All right, so boron is a metalloid, right? And hydrogen is a nonmetal. We combine the two, you should predict that the molecule, or sorry, the compound is molecular. All right, so this one is sodium oxide. Is this one ionic or molecular? So sodium's a metal, oxygen's a nonmetal, so you'd predict this one to be ionic. And then finally, C2H4 is ethylene. All right, so carbon is a nonmetal, hydrogen is a nonmetal, so you'd predict the molecule to be, sorry, the compound to be molecular.